So welcome to lesson 15. We're back to statistics, z-scores, and normal distribution. In Unit 1, we introduced two basic measures of central tendency. The mean, which would be defined as the arithmetic average of the data set, same as the average, and the standard deviation, which we define as the average distance from the mean. Given these two descriptive statistics, we will learn how to put into perspective the location of individual data points within the overall distribution of values. All right, it's a lot to say, but bear with it. Okay, as explained at the beginning of the unit, absolute numbers are virtually meaningless, right? Without comparisons. So the age distribution in the United States shows that the mean age of 38.5 in 2016, so that was the average age, with the standard deviation of 23.1 years. Thus, someone who's 15 years old, I'm going to put that right here, I'm going to put some of this in. So let me put the mean in, which is going to be probably about here, which is 38.5. And let me put that 15-year-old in right here. And the distance here between the two is 23.5, or about 1 standard deviation. Now, somebody that is 62 is 1 standard deviation above the mean. So let's put that in. Somebody who is 62 is about roughly 1 standard deviation, which is 23.1 years above the mean. A little rough, but that's fine. Just want you to get the idea of what a standard deviation is and how it applies off the mean. Now notice this is 1 standard deviation below the mean. This is 1 standard deviation above the mean. So one of the fundamental statistical questions we ask is whether or not the data is unusual. A z-score tells us how many standard deviations away from the mean a given data value is. All right? So a z-score, and I want you to read, this is an important idea. This z-score here would be about plus 1 z's, meaning that 62 is 1 standard deviation or 1 z above the mean. Well, the z-score for 15 would be a negative 1 z, meaning that 15 is about negative 1 standard deviation below the mean. So a positive and a negative score are really different. And finally, it says when data values are normal, when the distribution is normal, meaning it's symmetrical, not skewed, then the data value is considered unusual if it corresponds to z-scores above positive 2 or below negative 2. In other words, if I get another z-score here, another 23.1 years, I'd be at about 85 years old And if I had another -1 z-score here, it would be very unusual because it's below 0, which is not quite possible, is it? But if it's above or below 2 standard deviations in a normal distribution, then it's considered unusual. So here's our last problem. How many, on this page, how many standard deviations are above or below the mean is someone who's 84? So if someone's 84, I don't know, they're up here somewhere, 84. They're obviously above the mean because the mean is 38.5. Now I'm going to find out how many years they are above the mean, which is just simply taking 84 and subtracting 38.5. So that gives us 45.5 years. So they are 45.5 years above the mean. So the distance from here to here in years is at 45.5. Now each standard deviation is 23.1. So one standard deviation is 23.1. So I'm going to divide this by 23.1. And when I do that, I get 1.96. Or 1.97. So somebody that is 84 years old is 1.97 standard deviations above the mean. And their z-score, by the way, is 1.97. I'll go over this a couple times because this is the important concept. You get this, you're really on a roll here. In this section, we're going to be looking at mainly normally distributed data. Recall from our last study, we had left skewed data and right skewed data. But in this section, we're going to be dealing with normally distributed data, in which the mean, median, and mode are all the same. Now, I just want to ask you a question. Think about it for a minute. How do you think the population of the United States, which one of those models is the population of the United States most resemble? Is it skewed left, skewed right, or normally distributed? If you had guessed that it's skewed right, you would be correct. Notice how the tail is on the right side. This is 1940, and we're going to look at more modern data and how this has changed in a minute. But we're going to use the same graph. The x-axis is bin data into age categories 4 years each. The y-axis represents the percentage of the total population that fits into that bin. And now we'll look at how it's changed. World War II ended after 1945. After the GIs returned home, they formed families and created babies at record numbers. The far left represents all the babies, and this group is called the baby boomers. The 1970s marked two new trends. Birth control pills became readily available, and women entered the workforce in record numbers. You can see how the demographics have shifted dramatically now from 1945. You actually study these demographics during your second project. But the next 30 years are going to be marked by a lower birth rate
and an increasingly elderly population. These present great challenges, Social Security and healthcare among them.
Okay, so we're back on a paper. It says here you got a 63 on a test. Is this bad? Now, before you jump to any conclusion, it doesn't say how many questions were on the test. Again, you're not dealing with a ratio, you're dealing with a raw number. So to answer this question, you need to know how the score compares to the rest of the class. Assuming the mean was 51, we now know that you scored above average. But the question is, how far above average? To answer this question, you need to know how spread out the scores are. If all the other scores are between 49 and 53, you did really well. But if a bunch of people got in the 90s and a bunch of people got in the 20s, well, then you kind of did okay, didn't you? And I'm going to go and show you a histogram of what this is really saying so you understand. In our first scenario, your score of 63 is not only above the average, but it's above all the other students that took the test. There's their scores, while your score is higher than all of them. It's hard to argue that a 63 in this case shouldn't receive an A. But let's look at a different scenario.
So this has the same average score of 51, and you had the same score of 63. Now there's a lot of scores below 63, but there's also a lot of scores above 63. Your score is actually kind of in the middle of the class. So while an A was applicable for the last scenario, it's more like a B minus here. So this just goes to show that we need to know the spread of the scores, not just the average.
Well, we know now that the standard deviation, which is the average distance from the mean, gives us a measure of the spread, which we need to know. We're going to assume in this case that it was 5 points, and the mean is still 51. So now we're going to determine how well 63. Is it good or bad? So here's our data, and this is how we calculate z-scores. And a z-score, I'm going to recall what a z-score is. A z-score tells you how many standard deviations away from the mean a given data value is. And data values is considered unusual if it corresponds to a z-score above 2 or below 2. So a z-score is how many standard deviations it is away from the mean. So to calculate it, it's right here. And a z-score is the data score minus the average, which gives you the spread that data point is from the average, the distance it is from the average, which in this case is going to be 63 minus 51, divided by the standard deviation, which is that S there, which in this case is 5. So we're going to have 12 divided by 5, which gives us a z-score of 2.4. So just to reinforce that, this means that your score of 63 is more than twice the distance above the mean. In fact, it's 12 points above the mean, and a distance of 12 is 2.4 times the average distance of 5 points. The number 2.4 is plus, and notice that plus because it's above the average. Is 2.4 times the standard deviation from the mean. So what grade should you get under this scenario? Hopefully you'll realize you should get an A. Show that somebody who got a 39 is 12 points below the mean and has a z-score of negative 2.4. And I'm going to do that on the next slide. So we're going to show that somebody who has scored a 39 is 12 points below the mean and would have a z-score of a negative 2.4. It's really important here as students make this mistake all the time. It is 39 minus 51. It's the data point minus x bar, and x bar is the mean, divided by the standard deviation, which is 5. So this is going to be a negative 12 over 5, which is a negative 2.4. Now hit pause and tell me what score you think this person deserves for a letter grade on the test. And if you said a E or a failing grade, be correct. Okay, so I'm going to run through these, but I strongly recommend that you hit pause before the answer comes up and work it out on your own. I'm giving you here the formula for z-score, which is not hard to memorize. It's just the score minus the average divided by the standard deviation. So we're going to assume a normal distribution. We're looking at USA students taking this assessment. The mean score, so what's the average, is 47 with the standard deviation of 28.8. So what would the z-score be for a raw score of 512? So hit pause and work it out, and I'll put it up here. And I'm getting a positive 0.87, round it. So what would the z-score be with the raw score of 455? I'm just going to start this and I'll put in the answer, but remember the 455 is the score. So it's the score minus the average divided by the standard deviation. And if you work that out, you'll get a negative 1.11. Notice the negative. Okay, what would a person's raw score be if their z-score was 0? Well, this gets to fundamentally understanding what a z-score is. So if your z-score is 0, then you don't know what the raw score is, but you're going to subtract the mean and divide by 28.8. Well, what does this have to be in order for this whole thing to be 0? And the answer is 487. Which makes sense because understand again what a z-score is. And let me put it up here again. A z-score tells you how many standard deviations away from the mean a given data value is. Well, in this case, the data value is 0 away from the mean. So a z-score of 0 corresponds to the average. Now, what about a z-score of 1? Now, I could do this algebraically, right? From the formula. I can say, okay, and I'll do it. I'll write this out. So there it is written out using the formula, putting in what I know and leaving out what I don't know. I'm doing this the algebraic way. It's not my favorite way of doing it. I don't think it provides understanding, but this is how you can do it. Now, what would I do to both sides of the equation here? And if you answered multiply by 28.8, you would be right. And the next thing I do would be add 487 to both sides. So why don't you work with this and see if you can come up with the correct answer. So voila, there it is worked out. I put in what I knew. I multiplied both sides by 28.8. I got this. And then I added 487 to both sides. And I got x equals 515.8. Now I'm going to leave this x equals 515.8 up here. I'm going to erase this and to show you an easier way of doing it. Now I'm going back to the original definition of what a z-score is. A z-score of 1 means that you scored one standard deviation above the mean. So that would be the mean plus 1 standard deviation. And add those together and you're going to get 515.8. So for number E here, doing it the way I just did it here, I could just simply go 487, that's the mean, but I scored 1.5, I'm going to take away 1.5 of the standard deviations. And I'm going to get 443.8. Now, if you want to do it formalistically with algebra, you could do it this way. Negative 1.5, because you know the z-score. I'm going strictly according to the formula up here. Negative 1.5 equals x, that's what I don't know, the raw score, minus the mean, which is 487, divided by 28.8. Again, you would multiply both sides by 28.8 and then add 487 to both sides. And if you want to try to work it out, you will get that. These questions kind of get at your understanding of a z-score and how it relates to the data set. So think about it before I put up the answer. A positive z-score indicates what? And a negative z-score indicates what? I'm going to give you a second, put it on pause, think about it, and I'll throw the answers up. So a positive z-score indicates a data value above the mean, because that's how you get a positive number in the numerator, right? Because you got the score minus the mean. So if it's score, if the data point's higher than the mean, you're going to get a positive z-score. And likewise, a negative z-score indicates a data value below the mean.
So I just want to review from last chapter the relationship between histograms, which are these bins down here, all these bins, and the normal curve, which is here. So when we make these bins smaller and smaller and smaller, if it's a normal curve, it'll resemble this bell-shaped curve here. So this bell-shaped curve is the normal curve, and it's derived from making bins of data smaller and smaller and smaller. Notice this is normal because of this information here. The mean and the median are almost the same, so they're right in the middle. And also you can see that the mode is pretty much the same too. So this is a normal distribution, and this is what we'll be talking about for the rest of this lesson. So when you have a data set that is normal, as seen below, a normal distribution, you can derive probabilities from the data. And we're going to look at the probabilities associated with the rule called the 68, 95, 99.7 rule. All right, remember that a bell-shaped symmetric curve is an approximation for many real-world data sets. In other words, this is like a perfect approximation. Not all data sets are just perfect, but this is what we're looking at. So a lot of things are normally distributed. Heights of people, housing prices, SAT tests, stock market price changes. So there's many things that follow the normal distribution, but of course there are many, many things that don't. So there's so many varieties of units, right? Like heights of people is inches and feet. Housing prices is dollars. SAT scores would be just a numerical value. Stock market prices is in dollars. So there's a lot of variety of units. So a lot of times we'll replace the data values with z-scores and discuss how many deviations away from the mean the value is. So in a normal distribution, 68% of the data, which is right here, 68% of all of the data will fall within one standard deviation, plus or minus one standard deviation, or z equals 1 to z equals -1 of the mean. This here is the mean. 0 standard deviations. So that's the 68. The 95% rule, you can see the 95 here, means that in a normal distribution, 95% of the data will fall within 2 standard deviations of the average. And the 99.7 rule, which is way out here, means that 99.7% of all the data in the data set in a normal distribution will fall within 3z, or plus and minus 3 standard deviations of the average. So it says IQ tests are one of the most validated tests ever devised by social scientists. In other words, they're extremely accurate. So an IQ test has an average of 100 with a standard deviation of 15. So there's the two things that we need. Now what we're going to do is use this rule that we just talked about, the 68, 95, 99.7 rule to answer these questions. And the first question is, between what two IQ scores would you expect 68% of all the data to be? So the 68% rule is one standard deviation, or all the data between positive 1z and negative 1z. And a z just stands for a standard deviation. So we have the average plus one standard deviation, and then we have the average minus 1 standard deviation. So you would expect 68% of the scores to fall between 115 and 85. If that makes sense. So between what IQ scores would you expect 95% of all the data to be? So 95% is plus or minus 2z. So I'm just going to take the IQ average and add 2 standard deviations. And then I'm going to take the average of the data, which is 100, and subtract 2z, or 2 standard deviations. So this would be 30 plus 100. And this would be 100 minus 30. So you would expect 95% of all the scores on an IQ test to fall between 70 and 130. And our final one is 99.7. Between what two IQ scores would you expect 99.7% of the data, which is 3 plus 3z, or plus 3 standard deviations to minus 3 standard deviations. And really the area under the curve, right? The little area, little square things, the area under the curve represents the data, right? So 99.7% of the area falls between -3 and +3 standard deviations. Likewise, 99.7% of the data falls between -3 standard deviations and +3 standard deviations. So let's just take our average and then add 3 standard deviations, which is 3 times 15, right? And then we're going to take our average and subtract 3 standard deviations. So for the 99.7, we would expect that would be 45, 145, and this would be 55, right? So 99.7% of all the data is going to fall between 55, an IQ of 55, and an IQ of 145. Okay, so I left our normal distribution here. And we're starting now with number D. And it says IQ scores below 100 represent what percent of all IQ scores? Now realize that this is 0 standard deviations away from the mean. So 0 standard deviations, or z equals 0, would be 100, and it'd be right in the middle. Now what is interesting about this normal curve is that if you draw a line right at 100, and you fold one side over to the other side, they would match perfectly. That's called symmetry. If it's spelled right. So it's totally symmetrical. For example, 1z, or 1 standard deviation above the average, we found out is 115 because we added 15. 1 standard deviation below the mean is 85 because we subtracted 15. So the amount of people between 85 and 100 is the same as the amount of people between 0 and 115 on their scores. So hopefully now you can realize that scores below 100 is the same as the amount of scores above 100, which is 50%. Scores between 100 and 115 represent what percent of all IQ scores? Well, this is the 68% rule right here, right? Between here and here falls 68% of all the data. So if 68% of all the data fall between there and there, that means 34% fall between 0 and -1, and 34% fall between 100 and 115. IQ scores above 145 represent what percent of all IQ scores? Now, if you recall from our last thing, 145 is way out here, representing 3 standard deviations above the mean. Now I'm going to erase this and talk about that just a little bit. So we're going to look at the percentage of scores above 145, which is 3 standard deviations above the average. Now recall that 99.7% of all data lies between 3 standard deviations. That's a key word, between, right? So that means if we take what's left, which is 0.3%, that means 0.15% is beyond -3 standard deviations, and 0.15% is above 3 standard deviations. So there's your answer, 0.15%. So if there's 230 million people in the United States, how many people would you expect to have an IQ above 145? Well, this is the same as finding sales tax, basically. You have 230 million. And you're trying to find 0.15%, which is 0.15 over 100. Put that in your calculator, and I get 345,000 people, which is a lot. It's a very high IQ. An important component of z-scores is they allow you to compare between different assessments. Many colleges require either the SAT tests or the ACT test for admission. You might remember taking one of these in high school. Of course, last year we didn't. So the mean, or the average for the SAT in Michigan in 2017 was 495 with a standard deviation of 105. Where the ACT test had a mean of 20.3 and a standard deviation of 5.8. So the question A is, Samantha scored a 621 on the math portion of the SAT test, while Chris scored a 27 on the math portion of the ACT test. Who did better? Well, we're going to find out who did better by comparing their z-scores. So the z-score for Samantha would be her score minus what the average score is, divided by the standard deviation. So we're going to get her z-score. Chris's z-score is going to be his score on the ACT minus the average for the ACT divided by the standard deviation of the ACT. So put that in your calculators and I'll put up the answer. So Samantha got a 1.2, z-score of 1.2, and Chris a 1.16. So who did better? Well, hopefully you realize that a 1.2 is going to be a little bit more than one standard deviation above the mean. And a 1.16 is a little bit more too, but it's a little closer. It's a little closer to 0. So the higher the z-score, right? The higher the z-scores, the further, the better that they did. So the answer is Samantha. Well, I showed up all dressed up for the last part that I'm doing here because I'm turning this over to Julie for her cameo appearance on the last page. So this is the last problem that I'm going to do, and I came live for it. It's the same problem, but in this case, Richard scored a 480 on the math portion of the test, of the SAT test, while Anna scored an 18 on the math portion of the ACT test. Decide who did better by comparing their z-scores. So we're going to take Richard's z-score first. It's always his score minus the average. And then you take that, divide it by the standard deviation, which in this case is 105. And we'll get that in a minute. For Anna, it's her score minus the average divided by the standard deviation, which in this case is 5.8. Now we'll put that on our calculators. And for Richard, I gotta look, well, importantly, negative. Why? Because you scored below the average. Negative 0.14 is what I'm getting. And now let's do Anna. And for Anna, I'm getting a negative 0. Look over there, 40. Now who did better? And the answer, hopefully, you would see is Richard. Because this score, although negative, is closer to 0 than this score, which is further away down this way, away from 0. So that's one way to look at it. This number actually also is larger than this number.
Great job, Peter, explaining z-scores and normal distribution and the 68, 95, 99.7 rule. Thanks for letting me do question number 6. Recall the following example from lesson 10. So if we go back all the way to page 37 from lesson 10, we had Gary who was interested in buying paper towels and having them delivered through Amazon during the pandemic of 2020. The main thing that we got out of this one was how to read that histogram there. We had 26 packages of paper towels. This histogram was skewed left. We had a median of 6. The middle number was 6. Our mode was also 6. It was the most frequently occurring number. All right. So we're going to use that data and we're going to expand on it a little bit. Towards the end of the pandemic, the number of days it took Gary to get his paper towels decreased. This means he received them what? Quicker or slower? Good job. He received them quicker. This is an updated histogram after about 10 months. So the original data up here was 26 weeks, and then we added about another 12 weeks into it. So we have a total of about 38, 26 and 12 is 38. So this is about 38 weeks, which is about 10 months. Now, if we look at this information, is this updated data, is it skewed right, skewed left, or is it normally distributed? Well, remember our data from up here kind of had a tail going to the left, right? So this one was what? Skewed left. But this one here, if I were to connect the dots, it's not 100% clear that it's skewed left or skewed right. This is more of a normal distribution. So we're going to say that this is normally distributed. It's a little bit off from normal, but it's close enough that we can study it as normally distributed. Now, let's go ahead and use some Excel formulas to calculate the basic stats seen in the chart to the right. So we have a chart to the right, and we're going to go ahead and calculate some of these basic statistics. We do not have an Excel file. An Excel file is not provided with the raw data above. In other words, you're going to have to create that, okay? You should easily, and this should be very easy for you, you should easily be able to recreate that raw data from the histogram. So let's go ahead and open up Excel, because you guys are going to have to turn this file in. So go ahead and open up a new Excel document. All right, so once I get Excel open, I can go ahead and put my data in there. There's a couple different ways I can put my data in. Let's determine which way is the easiest. I can make a frequency chart. If I make a frequency chart, the number of days till package arrive would be 1, 2, 3, 4, 5, 6, 7, or 8. And I'm getting that just from the x-axis here, right? The frequencies would be the numbers that are occurring on the top. So I have 3, 4, 5. The 7 means it took 4 days for the paper towels to arrive 7 times. I have 5, 6, 5, and 3. Now I can put those into the make a frequency chart if I want. Now that I have that information, is that easy for me to go ahead and calculate all of these things? Let's find out. So here I have my Excel file. Now it's really easy to calculate these numbers. I could calculate most of them besides the standard deviation by hand without too much trouble and just a calculator, right? The count would just be 3 plus 4 plus 5 plus 7 plus 5 plus 6 plus 5 plus 3. No big deal. My count is going to be 38. I have no problem giving you guys the answers to these. The key here and the purpose of this exercise is to be able to use Excel in order to calculate these data points. Because if we had a much larger graph or a much larger data set, you're not going to want to hand calculate this. So we want to be able to take information from a histogram and be able to calculate all these things, and then also use sentences and use a little bit more advanced statistics to evaluate what's actually happening. So I'll go ahead and give you these answers here. I have no problem with that. The mean is going to be about 4.6. How did I calculate that? It took 1 day for 3 different packages of paper towels to arrive. So I have 1 plus 1 plus 1. Here I have 2 days for 4 paper towels to arrive. So I have 2 plus 2 plus 2 plus 2. And I keep adding that all up, and then I divide by 38. You could also do the multiplication of 1 times 3 plus 4 times 2 plus 5 times 3 plus 7 times 4, etc. to get that 4.6. When you add them up, you divide by 38. The median is going to be the middle number. The middle number, when you write everything out, is going to be between 4 and 5. Let me show you what I mean by that. Sometimes it's easier to see it if you write all of your data out. So I would start with, I have 3 1s. I have 4 2s. I have 5 3s. I have 7 4s. right, I was just able to squeeze it in there. Now, if I wanted to calculate the median, the middle number, all I got to do is find that middle set of data points. If I have 38, that means I'm going to have how many on the left and how many on the right. That means I'm going to have 19 on either side. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Let's count from the right to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Look at that. So these two numbers here are my middle numbers. Okay, you can go through and cross them off if you like to make sure that's it. But I have two numbers here between 4 and 5. So what happens if I'm trying to find the median and I have an even number? I have to take the average. 4 plus 5 is 9. 9 divided by 2 is 4.5. Now this is tedious to do by hand. So why don't we just let Excel do it for us? Okay, so let's go to Excel. How do I have it calculate the count for me if I have my data in this format? Is it possible? Equals the count. What is my data going to be? I know I should be coming up with 38. If I do this, is that giving me a count of 38? No, it's giving me a count of 8. Why? What am I doing wrong? Oh, this is just 1, 2, 3, 4, 5, 6, 7, 8. That's where the count of 8 is. If I want to get the count, I need to do what? Maybe my count is the sum of all of these. There it is, 38. How did I get my mean? Well, I bet you when I multiplied these and then I divided it, I bet you it's 174 divided by 38. Now you're probably looking at me and saying, Julie, why are you doing this so complicated? It's a lot easier if you enter the what? If you enter the raw data, all of these become much easier to enter. Let's go ahead and check that out. So instead of entering the summary of data, why don't we try entering all of the data? And where do I grab all of the data from? Well, I'm just going to grab it from right here. I have 3 ones. And yes, it's going to take some time to put the data in, so go ahead and make sure you're getting the data in properly. And the reason we're putting all this data in is because once we have raw data in there, and you can see all my raw data here, it's going to be a lot easier to calculate some of this stuff than to calculate it from the summary data, and the summary data is over there. Okay, so let's look at this raw data. If I want to do the raw data, I do equals the count, and I put in the cells for the raw data, which I think is G2 to G something. Yours could be in a different spot, it doesn't matter, right? Yours doesn't have to look exactly like mine. So I get 38, look how easy that was, equals the mean of what? All of my raw data. Look how easy this is. What did I do wrong? It's telling me pound name with a question mark. It's saying it doesn't like it. What did I do wrong? Who can tell me? Very good. Mean is not a function that Excel recognizes. What do I have to use instead of mean? I have to use the average. Very good. Okay, I'm going to keep just 2 decimal places. Let's make this a little bigger. Let's keep just 2. You know what? Let's just go with 1 decimal place. The median. So you guys should go ahead and finish calculating all those, and I will go ahead and post the answers. I'm not going to do all of them for you. You should be able to do them. Again, it didn't like median because I spelled it wrong. Be careful, guys. I'm having a hard time today. All right, so you should be able to calculate the rest of these using Excel. What I'm looking when I grade your Excel file is I'll be looking to make sure that all of these are formulas. So don't just go in there and type in the mode, which the mode in this case should be 4. I don't want to see a 4 typed in there. I want to see the formula for that. Okay, so go ahead and finish typing in all of your formulas here, and I'll show you what the answer should be. Okay, so down here I have my answers of the outputs that you should be getting when you put your formulas into Excel. When you're done with Excel, you're going to want to go ahead and save this file, and you're going to end up submitting it to Canvas at the end of the lesson. Now, I have my answers here also. I rounded my standard deviation to 1 decimal point. You guys can leave it as 2 if you want, but for the rest of the questions, we're going to use just 1 decimal point. All right. Now, if you're struggling to figure out what formulas go in these spots, go back and refer to Lesson 9, page 30, because that has some useful information if you've forgotten how to put it into Excel. Now let's go back to the worksheet. All right, so the next question says to use the standard deviation in a sentence. Well, my standard deviation is 2. Remember, it was 2.06, but we rounded it to 2. I want a better sentence than the standard deviation is 2. Yes, that's a sentence, but it's not very detailed. Let's try and write a better one. All right, so I have a lot written here. Let's take a closer look. It took an average of 4.6 days for Gary to receive his paper towels during the pandemic of 2020. The standard deviation of this was about 2 days, meaning it was pretty common for him to receive paper towels between days 2.6 to 6.6. Okay, so that's one way that you could write a sentence about the standard deviation and how it applies to his situation. Now, based on this updated data, this data for this 10 months, what is the likelihood that it is going to take more than 8.6 days for Gary to receive his delivery? For us to do this, it's probably going to help if we draw the normal bell curve and write the mean and standard deviation like Peter was doing on some of the previous examples. All right, so here I have our bell chart up here, or our normal distribution chart. We want to go ahead and we want to put the mean in. The mean is 4.6. The 0 stands for what? The z-score. Remember, my z-scores are 0, 1, 2, 3, and they also go -1, -2, -3. Is what I'm going to do is I'm going to put my mean in, and since my standard deviation is 2, we're going to add 2 to each one, and we're going to subtract 2 to each one to get my values down here. So 4.6 plus my standard deviation of 2 means I'm going to be 1 standard deviation above the mean when I have 4.6 plus 2, which is 6.6. If I add 2 more onto that, I'm going to be at 8.6. And if I add 2 more onto that, I'm going to be at 10.6. Now I can go in the opposite direction too. 4.6 minus 2 is going to give me 2.6. 2.6 minus 2 is going to give me 0.6, and that minus 2 is going to give me -1.4, which doesn't mean much to us. So is what we have going on here is if we put in our 68, 95, 99.7 lines, there's that one right there represents my 68%, right? Because we have your 68, 95, 99.7 rule. I can have 95% of my data fall between 2 standard deviations above and below the mean. And I'm going to have 99.7% fall in that last group of 3 standard deviations above or below the mean. So hopefully you guys have gotten pretty good about this. Is what we're looking at is this very first one. Based on this data, what is the likelihood that it's going to take more than 8.6 days for Gary to receive his delivery? Well, 8.6 falls right here. So we want to find the area under the curve for just this part above 8.6. Well, what we know is we know that the whole area under the curve, you kind of have to think of it as a picture, right? The whole area under the curve is 100%. We know that this middle piece here, this middle piece right here, all of this, and it's hard for you to see and me to draw, but all of this right here, that's what? 95% of the data. So if this is 95% and this whole thing under here is 100, we have this piece plus the 95 has got to be 100%. Well, because it's symmetric, these two pieces are equal. So 100% minus the middle 95 gives me 5% between the two wings. Half of 5% is 2.5%. So we know that this area underneath the curve represents 2.5%. So therefore, 8.6 days, the likelihood it's going to take more than 8.6 days for Gary to receive his delivery is just that 2.5% chance. So it's only a 2.5% chance of him taking more than 8.6 days for him to get his next delivery. Now let's take a look at the next question. What is the likelihood that he is going to receive his next delivery in 2.4 to 6.6 days? Let's change this 2.4 to 2.6. Okay, I think that was a typo. So 2.6 to 6.6 days. Well, 2.6 to 6.6 falls where? Between -1 and 1 standard deviation. So that is just going to be the what? The 68%. It falls in that 68%. So the likelihood he's going to receive his next delivery in 2.6 to 6.6 days is 68% chance. All right, here comes the last question. Calculate the z-score for Gary receiving the paper towels 3 days from when he ordered and explain what this means in a sentence. So first we need the z-score formula. The z-score formula, remember, is x minus x bar divided by s. X is the data value, x bar is the mean, s is the standard deviation. Well, my data value in this case is going to be 3. My mean up here is 4.6, and my standard deviation is 2. If I plug that in my calculator, I should be getting -0.8. Now we need to understand what this means. Let's go back and let's look at the definition on page 15. A z-score is going to tell us how many standard deviations away from the mean a given data value is. Assuming the distribution is normal, then the data value is considered unusual if it corresponds to a z-score above 2 or below -2. So what we're looking at is we're asking ourselves the question as to whether or not the data value is unusual. So what we're trying to figure out is this value of paper towels taking 3 days, is that a usual or an unusual occurrence? And well, because we're getting a z-score of -0.8, as long as it falls between -2 and 2, which -0.8 does, then we can consider it as usual. Only if it's outside of these values, above 2 or below -2, is it considered unusual. So this means we are less than 1 standard deviation below the mean. This would be a usual time frame to receive paper towels since it's within the 2 standard deviation of the mean in either direction. I hope you guys enjoyed this lesson. Great job, and I'll see you guys next lesson.